All right. So yeah, I mean, welcome everyone. Where we left off yesterday was talking about Dijkstra's algorithm, right? And we went through the proof of correctness. Afterward, there was a couple questions that I thought maybe it was worth clarifying. So one thing was what is going on with this decrease key operation, right? Because it feels like we've already changed the distance value in line 10. So why do I do this decrease key in line 12? And so that's just like updating the corresponding data structure. You can kind of think as the dist values as being maybe stored in an array, but then I want to make the corresponding update in H, which is my data structure. And so for that, it takes in the three pieces, like what's H, like the data structure H, the key that I'm going to change the value for, and then the updated value for that key. So if we think about in terms of runtime of this algorithm, we've gone through correctness. It's going to depend on these main data structure operations, right? We've got the make queue operation, this delete min operation, and then this decrease key operation. And so to figure out the runtime of Dijkstra's algorithm, we'll have to figure out the runtime of those operations. Okay. So this was our proof of correctness, and now let's go through the runtime. So at a cursory glance, the runtime looks a lot like breadth first search, because basically I delete the vertices off of H one by one, and I loop over all their neighboring vertices, all the edges, right? And so you might think it's just big O V plus E. But because of those data structure operations, no longer am I just popping off the front. I'm now having to find the minimum value among the distances. And so that's going to cost me something, right? It's no longer an order one operation in general. And so we have our main operations are going to be V delete min operations, right? We add all the vertices to H to start, and then we delete them one by one. We have V insert operations. That's just at the beginning to make the queue. We insert them one by one. I'll talk about that a little bit after. There's like a kind of a way that you can make some of these queues just in a combined manner rather than inserting vertices one by one into it. Maybe people have heard of this heapify operation, for example. And then there's the decrease key operations. And in general, let me just go back up for a second. We do decrease key in this loop over edges, right? And so again, the U we delete here, we then loop over all its outgoing edges, UV, and then we're potentially doing a decrease key on every edge. We may do not, maybe sometimes we don't decrease the key because we didn't find a better distance, but to upper bound it, we say we do at most the number of edges, decrease key operations. So now we just have to figure out what's the runtime of each of those operations. The simplest implementation of a priority queue is just store it as an array. Just it has n entries, right? Where entry 1 is distance to vertex 1, entry n is distance to vertex n. If we think about that, then we have our three operations to perform in it. So the first one being delete min. What's it cost to find the minimum element in an array of length V? Order V, right? You just have to go and inspect each entry. It's not sorted or anything. You just have to go and inspect each entry and find the minimum, right? So delete min, if we use an array, will be a big O V operation. Insert. I mean, this depends a little bit on like the implementation, but in general, if I'm just inserting things onto the back of an array, like growing it by length 1 at each time, that's an order 1 operation. It kind of depends, like you may have experienced if you're trying to insert things on the front of an array, for example, this can actually be an operation that grows with the length of the array. But anyways, let's say it's just order 1, right? We insert it on the back. So we can create this array of initial distances in order V time. We can create all V distances. So this will be order 1. And then what's it cost us to do decrease key in an array? So I have an index and I want to update the value that's stored at that index. Order 1, right? I mean, you tell me you want to set dist of the 7th entry to a 3, right? You just go dist 7 equals 3. Like, so this is now an order 1 operation. So if we sum all these up, multiplying them by the number of operations we have to perform of each kind, we've got to do v delete min operations, each one being an order v operation. We have to do v insert operations, each being order 1 time. And we have to do e decrease key operations, each being order 1 time. So the dominating factor is going to be v times big O of v, right? In other words, accessing the minimum element each time. So that's the bottleneck if we use an array, is find that delete min operation. We have to do it v times, each time it costs us order v. The question then is, can we use a better data structure or a different data structure that allows us to do that more efficiently? And it's, I mean, I'm sure some of you are very familiar with data structures, but it's kind of like cleaning your room so that you can find something more easily, like your keys or something. I don't know, whatever, right? And you actually spend some time every day or whatever to clean your room or to keep it clean, but in doing so, you can then access your keys more quickly. So there's kind of an overall overhead to everything, but that one operation that's like your bottleneck is now faster. So that's exactly what like a priority queue is going to do. We'll be able to do delete min faster at the expense of actually doing insert and decrease key slower, because we have to do more bookkeeping to keep everything organized. Did you have a question or no? Okay. Okay, so using an array, Dijkstra's algorithm runs in v squared time. The other option is called a binary tree or min binary heap, where first, what's a binary tree? So a complete binary tree is a tree where each vertex has 2 children, or at most 2 children, a left one and a right one. There's kind of a logic to the tree in that you have to fill up each level of the tree before you go to the next level. So top level contains 1 vertex, then 2, then 4, then 8, then 16, and so on. And there's an ordering enforced, which is that the value stored in an entry is always smaller than the values of its children. And in other words, what that means is that the min value is stored at the top of the tree. Its 2 children are larger. I don't care which is larger between the left child and the right child, just that it's the smallest and its children are larger. And then its children, the children's children are larger than it, right? And so it goes down in this fashion. So let me draw an example of a binary tree, just with some, I'm going to put the values inside the bubbles, like that are stored. So let's say, oops, I'll go with black. 4, 7, 9. I mean, the numbers in particular are arbitrary, just you'll notice that each node is smaller than its children. And then maybe there's the next level has just 1 vertex in it. Let's say it has, I don't know, 21 stored in it. So if I could maintain this, then delete min is now easy, right? I just pull the element off the top of the tree. like the root of the tree. But now, if I want to insert something new into this tree, I have to make sure that it still satisfies this property that its children are larger than the parent, right? And so I might have to do some operations to clean up the tree after I insert a new node into it, and also after I do a decrease key operation. So if I want to insert a new element into this tree, the way to do it, I'm kind of just describing it at a high level here. There are definitely some implementation details to work out. All I do is place it in an open spot on the bottom layer, and then I bubble it up the tree. So I check, is it bigger than or is it smaller than its parent? If it is, it's not in the right spot, and I swap. So let's just let me draw an example. Let's say I put, I don't know, 13 right here. So I'm inserting 13 into the tree. Now I check, is 13 larger than 40? No. So now I swap. 13 and 40 change place. And then I do another check. Is 13 larger than 9? Yes. And so it settles in that spot. So to insert 13 into the tree was one, just kind of place it at the bottom and then do one swap. If the tree contains V elements in total, then the depth of the tree is going to be log base 2 of V, right? Because it has a branching factor of 2. And so the total number of operations I would have to do is at most for 13 to propagate up to the top, right? And that would be just log V swaps. And so insertion costs, at most log V swaps must be performed. We do this idea called bubbling up. Decrease key, it's the same idea. Like, let's say now I don't know, I update a value. So maybe instead 12, we find a better path to it and I change it to a 6. Again, now it doesn't satisfy the min binary heap kind of property. And so I do a swap with its parent because 7 is larger than 6. They flip positions. And again, I have to do at most log V of these. And so this is a log V operation. So again, I bubble up and it takes log V. One thing you might be wondering about is this tree in itself is not really like enough information. Like the tree is the way we're storing it, but I also have to keep track somewhere of like, where are things in the tree so I can access them. And they usually call this a handle. So we store and update a handle, which actually can just be an array that kind of tells you the address of each vertex in my data structure. And then I have to kind of modify the data structure and then just modify in that array, where are things located. So that's why I'm saying this is kind of like a high level description. There are some definite implementation details to be worked out, but this is the idea behind a min binary heap. Delete min is easy, almost. So if you think about what happens, we want the min that's in the tree. It's just going to be 4, right? So we return the root. But now again, we've messed up our tree because we took the root off of it. So the way that you do it is you take 4 off, then just take a node from the bottom of the tree, put it on top, and let it sift down. So swap with its child if its child is smaller. So it would look something, right? If I popped 4 off the top, then maybe I put, I put 21 on top. And then we have 7, 9, 18. I guess this is now, well, let's just say it's 12. I didn't change it. And so now that, this doesn't satisfy the binary heap property. So I let it sift down by swapping with if both neighbors or both children are smaller, then I can swap with either one. And so maybe I don't know, let's say I swap this way. And then I have to do another swap here. Right? And it'll eventually settle in a spot where it satisfies the properties. So to do delete min, return the root value, and then to fix the tree, take a vertex in the last layer and place it at the root and sift down by swapping with the smaller children. Again, since the height of the tree is log v, I do at most log v swaps. And so the runtime is order log v. Yeah. Oh, sure, yeah. Just to the picture. Oh, you're right. Yeah. Thank you. Yeah. So what was just said is that I should have swapped. I have to swap with the smaller child, right? To make sure that the actual smallest element gets up to the top. Because what I did, when I swapped with 9, then 9 is at the top, but 7 is smaller, right? So I should have actually gone down the other side. Like that. So you should swap with the smaller child, you're right. It said that in the text, but I didn't do it. Okay, so now what's the runtime, right? We just have to add up the 3 operations. We know they're now actually all log v operations. So our runtime becomes so runtime of Dijkstra is going to be, we have to do v, I mean, they're all log v, right? But we have to do v operations. What was the first one we talked about? I guess we have to do v inserts. We have to do v decrease keys, each one costing log v. No, sorry, v delete mins, each costing log v. And we have to do e possibly decrease keys, each costing log v. And so our overall runtime is just going to be big O v plus e log v. Okay. And one thing I was going to mention is in this way I'm talking about it, to create the h at the beginning costs me v log v time, right? Because I do log v inserts, each one costing me v time. You can see that's not the bottleneck in the runtime. Like I'm already going to get a v log v for doing all my delete mins anyway. So it's kind of fine, but there actually is a better way to do it. It's called Floyd's heap construction or heapify, where rather than doing inserts one by one, I kind of do it in a big, like a bulk operation to I create, I pass it all the keys and their values, and then it creates the heap for me. And it can do it in big OV time. Yeah. Yeah. No, it doesn't matter. Same, sorry, they're interchangeable in my mind. I think in the textbook, they call it a binary tree, but people often refer to it as a binary heap. And so that's sort of my, anyway, yeah, no difference. So anyway, you can construct the whole thing in order v time rather than v log v, but it doesn't affect our asymptotic runtime. And then there's one other data structure we won't go over, but it's called a Fibonacci heap, where you have to do some kind of fancier analysis where you look at kind of what's called the amortized runtime over all of your operations. So rather than like looking at each delete min operation separately and each decrease key operation separately, I look at the sum of those runtimes over the entire execution of the algorithm. And with a like fancier data structure, basically I can not have E times log V, I get that the amortized cost of all the decreased keys is just E. So on average, kind of it's only order 1 time per decreased key. In any case, we're not going to go through the details of it. You don't need it in particular for this course. But you can see you can get the runtime down to V log V plus E. So now there's no log V multiplying the E. Which now is like not looking that much worse at all than just breadth first search, right? Breadth first search was V plus E, and now we're getting V log V plus E. If the number of edges is significantly larger than the number of vertices, this may be kind of comparable in runtime to breadth first search. So anyway, that's Dijkstra's algorithm. So in Dijkstra's algorithm, I talked about this yesterday, we delete a vertex from H once it has the smallest distance among all those vertices that are in H. And the proof of correctness relied on this fact. Like it relied on, like we were able to prove that that distance had to be set correctly at the time it was deleted. If some of our edges have negative lengths, this may no longer be true. And so there was a few questions on Piazza about this like last night, but so let me just give you an example and then I'll tell you just a little bit more about this. So let's take a simple, like super simple graph, just has 3 vertices, S, A, and B. The distance or length from S to A is 3. From B to A is -2. And from S to B is 4. So if we look at our priority queue, H, I'll write kind of the key value pairs, right? So when it gets initialized, the distance to S is 0. So we have S and its corresponding distance is 0. We have A and its corresponding distance is infinity. And we have B and its corresponding distance is infinity. Right, assuming that we call Dijkstra's on the start vertex. So now we delete min, right? S comes off and we do the update. So we'll compute and we find a new shortest path to A, which is going to be the dist of S, which is 0 plus 3. So A gets set to 3, B gets set to 4. S is gone because it got deleted. So A gets set to 3, B gets set to 4. And now we delete min again. It's going to be A, which is 3. And we now update its outgoing edges. It doesn't have any. And now there's just B4 remaining in it. And then we update B, you know, the outgoing edges of B. We find a better path to A, right? We've now actually found a path B is 4 minus 2. We find a path of length 2 to A. We go to decreased key. And our algorithm kind of chokes because H doesn't contain A anymore, right? We found a better path to H. Or sorry, we found a better path to A after A had been deleted from H. And so I kind of am breaking it with a technicality in some sense, right? Like I'm showing you that at the point that a vertex is removed, when there's negative edge lengths, its distance might not be correct. But you might then just say, okay, but what if I don't, like, what if I use kind of a different data structure where I just keep updating the distances even after, like, so, you know, it doesn't fail in this kind of case that I can't access it anymore. And so that's what the very last question on the assignment is asking you, can you still make it fail? Like suppose that the dist values keep getting updated. In this case, actually, everything works out, right? A gets set to 2, and that's correct, and then the algorithm terminates. But you can still construct an example. So it's not like there's a simple fix to Dijkstra's algorithm to make it work with negative edge lengths. It's actually like fundamentally flawed when there's negative edge lengths. So the question asks you, this is an example where it kind of failed due to the accessing the priority queue or an element in the priority queue that wasn't there anymore. But even if you fixed that, it still wouldn't be correct. So I'll just write here, A was deleted from H when dist A equaled 3. A correct value is dist A equals 2. Yeah. No, I mean, so first of all, Dijkstra's only applies with non-negative edge lengths. So then the graph can have cycles, anything. When you have negative edge lengths, you're exactly right that there's some issues with cycles. And in particular, cycles where the sum of the edges around that cycle are negative. And so we'll talk about that part in a second. So anyway, I guess just to repeat what I said, that last question on the assignment isn't asking you to just repeat this, because this is one where it kind of fails due to a technicality. I want you to just like make a bit better example where actually, even if I kept updating the dist values, it's still at the end of the execution, the dist values wouldn't be correct. Okay. So how do we fix Dijkstra's algorithm? The truth is there's no easy fix. We kind of need to do something different. And the core thing that happens in Dijkstra's algorithm are these updates. So in an update, you take in an edge, UV. I guess you're also, I'm kind of writing it informally, right? You take in the edge and you take in the dist values on the endpoints on U and on V, and you update the distance to V based on the distance to U, right? You perform dist V is the min between its current value and this new path you found that goes via U. So you have U, you have an edge from U to V, V, you have an edge length on it, and you perform the update on that edge. And that's like the core ingredient of the algorithm, right? It's repeatedly performing these things. And there's really just two possibilities that can occur. One is if, well, so the properties of this update. So it gives the correct distance to V if U is the second last vertex on the shortest path to V and its distance is set correctly. Right? If on the true shortest path to V, U comes right before it, and I had dist U correctly, then the path length to V is just going to be dist U plus LUV, and that's what I set it to in this line. And the other thing is that if it's not the shortest path, then I just update, like if dist U plus LUV isn't actually the shortest path, like the shortest path goes through some other vertex, then I'll just update dist V to a value that's larger than its true, shortest path distance. So dist V is always an overestimate, or it's correct. It can never go below the true value. And so the reason that's important is it basically means that doing updates on edges can never really hurt me. As long as I initialize them all to infinity and initialize dist S to 0, I could just go crazy, just perform updates on all the edges over and over again, and nothing can go wrong at least. They'll always remain an overestimate. And in some sense, that's exactly the algorithm that we're going to use for negative edge lengths. We just kind of we brute force just start updating all the edges a ton of times. And eventually we've done it enough that actually all the distance is propagated correctly through the graph. So that's what I'm going to like talk to you about now. But let's think about that idea. Like what has to happen for a distance to get set correctly? So let's say I have some vertex V. And it has a path from S, a shortest path from S to V. So we've got some S. Then let's say the next vertex on the shortest path to V is U1. Then it's U2. And then it goes along for a while up to UK. And then finally we get to V. So these ones are just direct edges. And then U2 to UK is like a sequence of edges. So we know that dist S is set correctly, right from the get-go. So it's correct at the start. Now, by property A up above, that means that after I do an update on this edge, U1 will get set correctly. I guess I'm using something here that I think maybe is intuitive to you, but I should probably just state, which is if this is an optimal path from S to V, then if I take any sub path, like let's say I go take the chunk that just goes from S to U2, that has to be an optimal path from S to U2. Otherwise, I could just swap in the better path from S to U2, right? And that would actually give me a better path from S to V. So always the property is that these subpaths of an optimal path are also optimal. That's like the kind of the key thing that we're leveraging in all of these algorithms. So that means, as soon as I perform the update on the edge SU1, U1's set correct. So and then let's say next I perform the update on U1, U2 after I've done this first one, then U2 is correct, right? And if I keep going, if I got this sequence of updates, so first I updated SU1, then I updated U1, U2, then U2, U3, and so on, all the way up to finally updating UKV, then dist V would have to be set correctly. So update UKV and V is set correctly. And I don't need them to incur like right one after another because by, let me just scroll up a tiny bit, by property 2, dist is always an overestimate no matter what edge updates are performed. So like, as an example, I could do update SU1, then do like 10 other updates on other edges in the graph, then later do U1, U2, then a bunch of others, then do U2, U3, and then a bunch of others, and so on. As long as I get that sequence, or a kind of subsequence of these updates, dist V will be set correctly. So it does not matter what other updates occur. just that this is, I'll call it like a subsequence, because I'm trying to emphasize that they don't have to occur one after another. Just, yeah.
Just to make sure, is this path the optimal path?
Yeah, yes. This is the shortest path. Thanks, yeah. Okay, yeah.
All these updates have to be done in order.
All you need is that the update SU1 occurs sometime before the update U1, U2, but not necessarily like right before it. But that sequence has to be somewhere in like your overall sequence of updates. So then if I think about that, right, like let's suppose now, what's my idea going to be? What if I just update every edge once? I'm definitely going to hit the update SU1 in that if I update every edge. Then update every edge again. In that one, I'm for sure going to update U1, U2. Then update every edge again, right? Now I'll get the update U2, U3. And the question is, how many times do I have to do that before I will have got the sequence for sure from S to V? And that's really akin to asking this question that I've written here, which is, what's the longest path in a graph, VE, that doesn't visit any vertex twice? Do you know the answer? So it has V vertices in it, and it can't visit anyone twice. How many edges could be on it? Pardon? So not quite. I mean, yeah. That's right. Yeah. Like, so for example, just as like a toy example, let's say you have a graph with 2 vertices. The longest path has 1 edge on it. If I grow it to 3 vertices, right, the longest path that doesn't visit any vertex twice has length 2. It's just like this one. Sorry, that was a bad edge. But exactly, it's V minus 1. So any shortest path uses at most V minus 1 edges. That means if I need at most this V minus 1 sequence of updates to get the right, the distance set correctly. So why don't we take a 5-minute break, because we've gone 40 minutes now, and then we'll come back to this. I'm going to pause the recording. So let's finish this, and then I'm going to just have a brief discussion about the midterm, because it's next Tuesday. So we basically have all the ingredients for the algorithm, so I can just present it to you now. And it's called Bellman-Ford. It takes in a graph along with edge lengths, assuming that there's no negative cycles. So I have to just tell you a little bit about negative cycles after, but for right now, let's say that there's no cycle in the graph where if I sum up the edges on that cycle, it adds up to a negative number. The reason being, then the problem doesn't make any sense, right? Because if I want to get from like S to some other place, and I could just keep going around this cycle and like accumulating negative distance, just go out around it an infinite number of times and get a distance of negative infinity. So the problem's not really well defined if there's a negative cycle. But all I do is same initialization I'm always doing. And then I repeat V minus 1 times because I know that's the longest that a path can be. And I just update all the edges in the graph. So iteration 1, update every edge. I know I got SU1 correct. iteration 2, do it all over again. I know I got U1, U2, and so I got U2 correct now, and so on. And that's it. And so I can add in prev pointers just as we did in the other algorithms, right? So I can keep track of the path that I found. And then this is exactly the logic, right? Is after the first iteration, dist U1 is set correctly. After k iterations, dist UK is set correctly. And so after v minus 1 iterations, dist v must be set correctly. And yeah, between the update of SU1 and the update for U1, U2, many other updates will occur because I'm looping over every edge in the graph, but that doesn't matter. They might modify the distance a bit, but they never change the property that it's an overestimate of the true distance. And so we can use this to prove correctness of the algorithm. And I'm going to say, like, basically, but through our discussion, this is essentially a proof of correctness. So I'm not going to go through all the details of the proof of correctness, but so runtime. Well, maybe so I mean, the runtime actually is pretty easy to write out. If update is an order 1 operation, because it just computes that min of dist v and dist u plus LUV, then what's this lines 4, 5, 6, 7 costing me? Yeah, v times e, right? I mean, v minus 1 times e, I guess, which is big O v times e, exact. And so that's exactly right. This algorithm runs in v times e time. There's the initialization, which was big OV, right? But this is obviously bigger. And so you can see, if I don't have negative edge lengths, I shouldn't use this because this is running much slower than Dijkstra's algorithm. And this is also why I think that last question on the assignment is kind of important, is if you think there's like a simple fix to Dijkstra's, it's just some way we're not updating the priority queue correctly, then like Bellman-Ford is a useless algorithm, right? If there was just a simple fix to Dijkstra's and I kept the same runtime of big O v plus e times log v, well, I'd never have to do this, right? So that's why I kind of want you to go through and figure out why it actually messes up sometimes. There's no simple fix. And I hope this insight is enough to figure it out, that like, I have to make sure I get that whole sequence of updates in order to ensure that dist v is correct. And with Dijkstra's algorithm, I can't really ensure that that sequence of updates occurs. Anyway, that's all I'll say about that. So let's go through one quick example, and then we'll have a midterm discussion quickly. So let me draw a simple graph just to illustrate. I think most of you are kind of getting it, but maybe just seeing it in action helps. So it's a graph with 4 vertices. Sorry, I have a lot of trouble drawing like smooth lines on a tablet. I don't know. So 2, 2, 10, and minus 20. Okay, and now I'm going to run Bellman-Ford. So if we go, sorry, just one second, let me skip up here. So I need to like just think about like what order I'm going to loop over the edges in that for loop, right? And then I'm going to repeat it a bunch of times. So let me just number the edges in some order. It doesn't matter, but just so that we know like how we're updating them. And I'm going to say, I don't know, this one goes first, then this one, then this one, then this one, then that one. Okay, I don't know. I just made it up, but it doesn't matter. So now let's keep track in a table. And it actually, if you think about it, so how many vertices are there? There's 4. So v minus 1 is 3, right? And then I have to update every edge. There's 5 edges. So there's actually going to be like 15 updates that happen. So if I want to make a table of this, I got to have 4 vertices, so 4 rows, and then 15 columns. So I'm probably just going to go out part of the way and then skip to the end because it's kind of a big table to draw. So we have vertex S, A, B, C, and then we have edge. And so it starts off with edge 1, then 2, then 3, then 4, 5, and 1, and 2, and 3, and so on. And let me just say to the end. So in the initialization, let's make one more column here that say that that's where we initialize everything to. We're gonna have 0, infinity, infinity, infinity. Now we update edge 1. And we find a path of length 10 to C, right? So after the update of 1, we have 0, infinity, infinity, 10. Now we update edge 2, and we find a path of length 1 to B. So 0, infinity, 1, 10. Now we update edge 3. That gives us a path of length 2 to A. 0, 2, 1, 10. Update edge 4. That gives us a better path to A, right? Because now we have C is 10. C here is set to 10, and we just subtract 20. So we actually find minus 10 to, I might have picked a good ordering, and we're going to get there a lot faster than all the iterations. But S stays at 0. I mean, S will never change in this case, unless there was a negative cycle. Now A, sorry, A went to minus 10. No, yeah, minus 10. B stayed at 1, C stayed at 10. Now we update edge 5. That found a new path to B, but it's not better, right? That path, oh yeah, it is better. Why am I saying that? Minus 10. The new path to B is going to be minus 10 plus 2, which is minus 8. And C stays at 10. And I think actually at that point, the way I'd written it in my notes, I think I'd like numbered them differently, and it took more iterations to get the correct distances. But I think we're actually correct already. So now it's just going to do a bunch more updates, because I've really only done one of the 3 loops through all the edges, and nothing will change actually. So it'll just keep going like this. And these I think are the final answers, unless I'm missing something, right? 0, minus 10, minus 8, 10. Any questions on that? Did that make sense? I think I've poorly picked the edge ordering to make it potentially confusing, but. Okay. So briefly, I guess, midterm. So midterm's on Tuesday, just so everyone, I think most of you know, but I posted the midterm from 2020, which was the last time it was in person, on Learn. So take a look at that. That's definitely like format wise, that's very similar to what the format will be. Like 10 true or false, followed by a few questions, right? Kind of covering analysis and design. What else did I want to say? So it will cover basically up to the end of Dijkstra's algorithm. So you can look at Bellman-Ford, but I'll post on Learn if I'm saying something wrong, but I'm 99% sure there's no question on Bellman-Ford in there. It doesn't go that far. I guess the one other thing I would say is, so in questions, right, they'll ask you to design an algorithm. And the biggest thing to communicate is that like you understand the idea. So like, for example, if you look back at the midterm from 2020, there was a question where the answer was basically do binary search. It was in this one where you're trying to find like where it was an array of zeros followed by ones, right? And you're trying to find where's the first one. And the idea was do binary search. And if you're short on time, like you should just kind of write, do binary search on this, you know, like search, if it's a 0, then search in the left half. If it's a 1, then search in the right half. Don't worry about trying to like get all the indices correct, you know, like you've got, you know, because you actually want to implement binary search, it's a little bit complicated. You have to keep track of the mid, the left, the right, and do all these updates. And maybe you'll lose a point or something, like if it's really unclear how it would be done, but you'll get most of the, if you're showing the idea, you'll get most of it, right? So I guess that's the only thing is I notice in the class, some people like, will even try and write like C code almost, you know, for like the pseudocode, and it must take a ton of time, and it's and then it's actually hard to figure out the idea in it sometimes, right? Because it's so like detailed that you don't actually get like, did they know that it's just sort of a binary search idea? Or so like, anyway, start at the high level is all I'm trying to say. And then if you have time, fill in more details, but make sure you get your idea down. Yeah. Not really, no. No, mostly like asymptotic runtime type questions. The one other thing I was going to say is just because of like the pandemic and us wearing masks and all this stuff, normally like I walk around and people put their hand up and I can like kind of, you know, squeeze through the aisles and answer a question by like leaning in. I think we won't do that because some people might not want to do it, and then I think it's just not great. So we'll just say no questions in the exam. Like I won't answer any questions. So if you're unsure about something, just write your assumptions and continue, you know. You can take a bathroom break, like we'll have TAs to like take people to the bathroom or whatever if you need, but anyway, I think it's the simplest way to proceed. Any other questions on the, yeah?
Just to be sure, so for a design question,
I would say pseudocode will get you full marks, like pseudocode though, like what we do in the class, not like writing in a particular language, but getting the idea down may get you full marks if it's sufficiently clear, and will definitely get you good part marks. So like you'll probably notice, right, even in the 2020 midterm, it's kind of long. And if you're trying to write out really detailed pseudocode to everything, you might get stuck on a question and not even get to other ones, right? So that's all I'm trying to kind of giving you like advice on optimizing your time in some sense. And the one other thing, I guess, you'll probably also notice on the midterm from last time is 2 questions of equal point value aren't always of equal difficulty, right? So kind of like, you know, go to some questions should be easy, basically, right? And like make sure you pick those off before you spend, because there might be a question or 2 that are kind of hard as well. And you don't want to like blow 30 minutes on that and then not answer the easy one that was just like free points almost. So anyway, that's all my exam advice. Any questions on that? Any other questions? Or okay. Let's finish this up then. So we've got negative cycles. So I kind of mentioned that. What's the issue with negative cycles? Well, let me just draw a simple example. Let's say we have 4 vertices again, A, B, C, and S. And they're 1, 1, -3, 1. Then this cycle right here has the sum of the edges around it is -1. And so the shortest path problem isn't really well defined. For example, if I want to find the shortest path from S to B, I can go S to A, go around ABC 10,000 times, I get -1,000, and I get an answer of -999. If I went around 1,000,000 times, I get an answer of, 1,000,000 minus 1, or minus 1,000,000 plus 1, sorry. Yeah. Yeah, if you had if there was a variant of shortest path where you couldn't visit a vertex again, then that would be well defined. That's right. We won't really cover that in here, but you're right. Yeah. So the point is that I can keep going around a cycle, get a path that uses an infinite number of edges and achieves a cost of minus infinity. So one thing though, again, is like visually we can see here that there's a cycle of negative with negative length, or a negative length cycle, but detecting one in a graph is kind of an interesting question. But Bellman-Ford exactly allows us to do that, because I update all the edges v minus 1 times. If the graph didn't have any cycles, I should have all my distances set correctly. So if I just do one more update of every edge, if a distance changes, there has to have been a negative cycle. Because if there was no negative cycles, I would have found the shortest path to every vertex and nothing should change. So if the distances changed, then there's a negative cycle. If the distances don't change, then there couldn't have been a negative cycle, because they're not going to change on the next update again, right? Like nothing, if nothing changed for one update cycle of all the edges, the next one I do is identical. I have all the same distance values. I do all the same calculations again, I get no update again. So all I do is I can just modify Bellman-Ford, where instead I perform v iterations instead of v minus 1. And then if I check if some dist value changes in the vth iteration, then there's a negative cycle. And then you would kind of output shortest path problem doesn't make sense on your graph, something like that, right? That's. Okay, last topic, which is a short one, is if I want to compute a shortest path in a directed acyclic graph, I can actually do it more efficiently, even with edge weights. Since there's no cycles, I don't have to worry about negative cycles or anything, right? Because it's an acyclic graph. So, but the key thing in a directed acyclic graph is that we can topologically sort the DAG. And remember, in a topological order, every vertex points to a vertex with a higher number in the order. And so that means every path has to follow the topological order. Right? If I take any path in the graph and I look at the order number set on every vertex, there'll be an increasing order. And so that means I can just do updates. I can update all the edges leaving the first vertex in the order. Then I update all the edges leaving the second vertex in the order. Then the third, then the fourth, right? I just loop through them in topological order, doing the updates, and I'm sure to get the sequence of edges that appear on any path. So in a DAG, in a directed acyclic graph, vertices appear in increasing topological order. In every path, right? In every path in a DAG, vertices appear in increasing topological order. And so I can take in a DAG with edge lengths. They can be positive or negative because there's no negative cycles to mess things up. I initialize the exact same as before. Then I topologically sort the graph. People remember, how do I topologically sort? It was a modification of one of our core algorithms. Yeah. Yeah, in which algorithm was I running? Yeah, exactly. Depth first search, right? We added these pre and post numbers. and then we sorted in reverse order of post number. So, and topologically sorting can be done where I can do, rather than having to run topological sort, or sorry, rather than having to run DFS and then sort the vertices, which would then be like a V log V operation to do the sorting, I can instead run depth first search. And as I write the post number of a vertex, I just add it to my list. You know, like I'm maintaining a list with the topological order in it. So the first one that finishes goes into the list. Then the next one that finishes, I insert it on the front of the list. The next one that finishes, I insert it on the front of the list, and so on. And in doing that, I can actually topologically sort a graph in big O V plus E time, just the runtime of DFS. That was what we covered. So this operation here takes big O V plus E using DFS with pre and post numbers. And then I loop over the vertices in topological order. I process all the outgoing edges from each vertex, and I do the update. And so this loop is just running in the number of edges. I guess technically it should be probably V plus E, because even if there was no edges in the graph, I loop over all the vertices. But and so I guess I kind of labeled the runtime on the pseudocode, but the runtime is then big O V plus E. Yeah. I was kind of being lazy. I should have written V plus E here. I'm sorry. Yeah, I kind of like wrote E and then I realized I should have. So you're not wrong. Like it's. No, I mean, you might as well absorb it in, because you don't know, like the graph might not even be connected. Like it could have 100 vertices and only 2 edges, in which case V is the bottleneck in that second thing. I was just kind of being coarse because we already had a V plus E above it. And then like, you know, in general, there's going to be at least as many edges as vertices. And so the second part runs in big O E. Yeah. I guess. I mean, I think they're all the same in the end, but yeah, I think max of V and E would be fine, actually. Then I'm going to add it with V plus E and get V plus E in the end anyway. Okay, and so shortest path in a directed acyclic graph can be found in big O V plus E time. Yep. Basically, because the input, if I provide the graph as an adjacency list, it already takes up big O V plus E space. So just to read it in takes me that much time. So just to briefly summarize our algorithms and their runtimes, we had breadth first search and depth first search, both big O V plus E, right? Linear time, essentially, but they don't handle edge lengths. Then we had Dijkstra's algorithm, which takes in any graph you like, but with non-negative edge lengths. And you can quote, you know, there's caveats there because now it depends how we implement the priority queue. But the typical one you'll see is the min binary heap. And so it's V plus E multiplying log V. If I have negative edge lengths and there might be cycle, like it's not an acyclic graph, but there's no negative cycles, then I have to go with Bellman-Ford. That's big O V multiplying E, which kind of E can be V squared, right? So that might be V cubed in the worst case, right? And then if we have a directed acyclic graph with edge lengths, they can be positive or negative. I get back to my nice linear time, big O V plus E. Yeah. I think you're back to the case where you need to do Dijkstra's algorithm. The first time you find a path, the shortest path. Like, first of all, if it's not acyclic, you can't topologically sort it, right? If it has a cycle, it doesn't have a topological order. And so then I think you're just back to Dijkstra's algorithm. Yeah. But anyway, that's the end of our kind of graph algorithms coverage. So I guess last take home point is like try to always use like in your assignments and whatever, like if the graph doesn't have edge lengths, for example, you should be using BFS or DFS probably, right? Not Dijkstra's algorithm or Bellman-Ford. Even if they also would solve it, it's like overkill, right? You get a better runtime with an algorithm that's suited for graphs without edge lengths. So just like tailor your usage to the correct application, yes. Anyway, that's all. Thanks a lot. We'll stop there.